Hello my wonderful students. If you're watching this video, this is going to be a series of videos to show you how to draw the lines for both lenses and mirrors, as well as to figure out how to do the math and what variables stand for. At any point in this video, feel free to zoom back and forth to find what you need. I'm going to try to put in subtitles about what the different things are going to be doing so you have an easy way to figure it out. Both me and my wonderful director are going to guide you down to some wonderful physics. So let's begin. Situation number 1, concave mirrors. Take a look at this, the principal axis. I'm going to draw my concave mirror here, and I'm going to draw a focal point at some point there. And now I'm going to draw my object outside the focal point. I'm going to write object outside focal point. And we're going to draw 2 light beams here. The first light beam is going to go from the tip parallel till it hits the mirror. And when it hits the mirror, it's going to reflect, because of the shape of the mirror, through the focal point. And to keep going. The second light ray is going to go from the tip through the focal point till it hits the mirror and reflect parallel straight back. Your eye over here sees these 2 light beams, and your eye sees them as coming from this point. So this point is where your eye perceives the image from. That's your eye. This point is below the principal axis, so I'm going to draw it in like that. Let's label a couple things. This distance from the image to the mirror, I'm going to call di. And since this is in front of a mirror, that means this is a positive value. This height of the image from the principal axis is going to be hi. And since it is upside down, it's to be a negative value. This distance from the focal point to the mirror is f. And since for this kind of mirror it combines light, it's going to be a positive value. Using the equations 1 over f equals 1 over di plus 1 over do, and m is high over ho, which is negative di, or opposite of di, over do, you could solve for what's needed. In this situation, which can be different depending on where this is, we're going to say this is going to be a real image. Real image for 3 reasons. Number 1, this is inverted, real. Number 2, light is actually combining at that point, real. Number 3, this is in front of a mirror from where we expect. The consequences for real: hi is going to be negative because it's always inverted. Di is going to be positive because it's where you expect. Next up, this is inverted. Because it's upside down, hi we said is negative. And we're going to say that m is also negative. It has a negative magnification because it's upside down. And looking at this, it looks like this is actually reduced. The image appears smaller than the object. Because it's reduced, I'm going to say that absolute value of m is less than 1. Absolute value because the negative positive refers to the upside down, right side up. This magnification will probably let's say 0.6 or something like that. But the actual m is going to be a negative value because it's inverted. If you do the math, from these things you can go backwards to figure out if it's real or virtual, inverted or upright, reduced or magnified. And this is how you draw an object outside of the focal length. We're about to do another one right now, the object's inside the focal length. And welcome back. We're about to do our second case. Again, a concave mirror, but this time do is inside the focal point. Now, this is still a converging mirror, so f is still positive. But because we're forced inside the mirror, the light can't actually reflect outside. As you will see, this means this is going to make a virtual image. Let's draw our two light beams. The first light beam, again, parallel, then through the focal point. Your eye is again over here, looking at it. The second beam should be through the focal point, then straight. We can't make that happen. If I went from the tip to the focal point, it would never actually hit the mirror. So we're going to take the light beam like it's coming from the mirror, sorry, from the focal point, until it hits the lens or mirror, and then it's going to angle straight back. These two light beams kind of hit your eye, if your eye's over here somewhere. Your eye sees them as coming from somewhere over here. And to show that, we usually draw dotted lines to represent where it's perceived to come from. Here's our image. This is where it appears to have been made. In reality, this is happening in your brain. And your brain makes it seem like it's behind the mirror. Okay, is this a real or virtual image? Well, it's upright, so it's got to be virtual. In addition, it's behind the mirror. Light shouldn't go behind the mirror. That means it's virtual. And third, instead of light rays actually hitting that point and then going to your eye, in this case, the light rays are never coming together. So this is a fake point that your brain makes. It means it's virtual. So for virtual, HI is going to be a positive value. It's up some height. And DI, this distance, is negative. Why is it negative? Because it comes out mathematically and in words. This arrow is not where it should be. Light should be reflecting off a mirror. It should not be passing through. Virtual. It's upright. HI is positive then, and again, if this HI is positive, that means it's virtual, which means DI is negative. So you already have a little connection. And in this case, it's also magnified. I'm going to end up with a positive number that is greater than 1. At this point, you now can see that for a concave mirror, depending on where you put the object, you can have both real and virtual. Real is when it's outside, virtual is when it's inside. The magnification depends on a bunch more things. So it's not like magnified always means virtual. You can see here, it's magnified and even virtual, magnified real. With this done, we're about to do our third drawing situation for mirrors, and it's the only one for convex. Looking forward to seeing you. And welcome back. We're about to do a convex mirror. Now, in the previous example, I had to discuss whether the object was outside or inside the focal point. This is entirely different. This kind of mirror, because of its shape, scatters light. Because it scatters light, it has a negative focal length. And because it scatters light, it will always have the same 3 properties. We're going to see in a little bit. This is always going to make virtual, because it's scattered. And yes, that's lowercase and uppercase. Reduced, upright. This is always true for this kind of mirror. All right, negative focal length. Negative for mirrors is where it shouldn't be. It should not be on this side. So the focal length is going to be over here, with this distance negative f. I'm going to put my object here. It's not inside or outside the focal length because it's nowhere near the same side as the focal length. First ray diagram, going straight, parallel. Now it's going to hit. Since this is a fake focal point, it is a scattering point. Light does not want to go to it. Light wants to go from it. I'm going to draw my arrow lined up with that focal point. And then for my other light beam, I'm going to do the opposite. Instead of parallel, then from focal point, I'm going to kind of draw from focal point, then parallel. And to go parallel this way. Notice I did not extend it back. I only extend back the reflection. So here's your eye. You're looking at this. Your eye sees these two light beams. Again, trace them back. It looks like they're coming from somewhere over here. Extend back the reflection lines. And there you go. That's going to be my image. Now, quick note. Notice, it is physically impossible for this arrow that's pointing to the focal point to ever be higher than it starts. This will always reduce your image. And because of the scattering, it'll always be virtual and upright. Just a reminder, because I'm going to keep on hitting this point, virtual, you have a negative DI, a positive HI. Negative image distance, that's this right here. And you're going to have a positive image height, that little bit right there. Reduced means that M is going to be a positive value, positive because this is upright. And in this case, M is going to be absolute value less than 1. So an example of magnification may be like 0.75 positive, 75% of what it used to be. And it's upright. HI is positive. The same equations we learned before work. And whatever sign you get, you can use here and figure out these three things. But I'm going to have a big warning at you. And the warning is, if you have a convex mirror, the focal length is negative mathematically. Sometimes in physics, we're big jerks. We say like the focal length of the scattering or diverging mirror is 20 centimeters. If you see the phrase convex mirror, diverging, scattering, then you know to make that value negative. And it will make a huge difference mathematically. I'm talking very different numbers. You do not want to be caught that way. Well, that's in mirrors we have done right now. You're going to see that a convex mirror and a concave lens behave the same. So when we do concave lenses in a little bit, you're going to see it will also always be virtual, reduced, and upright. And a convex lens, like a concave mirror, will have both real and virtual, depending on the objects. So it's now time to look at the lens pictures. All right, now it's time for lenses. The difference between lenses and mirrors is a couple different things. First of all, as you may remember, lenses have got two focal points. Because of the fact that light bends when it hits a lens twice, there's one in front and one behind, whether it's real or virtual. Doesn't matter. Look at a convex lens. Because of the shape, this is a converging mirror. Converging lens, I'm sorry. So F is always positive. That does not mean you will always get real images from this. It depends on if the object is inside or outside the focal length. Let's do DO is outside the focal length. They're equally spaced as best you can. And I'll put it way out here. DO is from the object to the lens, technically the center, but pretty much it should be the same. This is the focal length. We're again draw two light beams. The first light beam starts at the tip, parallel, and then it hits the lens. Snell's law occurs twice, and we summarize it by simply making a bend in the middle. Now, since light should pass through a lens, it's going to pass through and go through this focal point, this special parallel line. The second light beam, we're going to draw from the tip, goes to the focal point, hits, and then refracts parallel. The light beams combine combined here. And of course, for a lens, you're looking at the other side. You have your eye, your glasses, and the thing you're looking at. You see both these light beams as coming from this point right here. That point is below the principal axis, so therefore it's going to be inverted. Just as a reminder, inverted means HI is negative, and DI is, well, for mirrors, this region was negative because light should not go through a mirror. But a lens expects light to pass through. So for a lens, this side over here for images is negative DI. This side over here for images is positive. And again, a positive DI means it's real. It's real for three reasons. It's real because it's inverted, check. It's real because light is actually combining from that point. And it's real because we expect it to be through a lens and not reflected on it. And because it's real, DI is positive and HI is also negative. And finally, in this case, it's most definitely reduced. M is negative because it's inverted, and M, absolute value, is going to be less than 1. Now, big pause. When you're outside the focal length, these two things are always true. But this one depends as well. You can have, by moving it forward, getting a bigger and bigger dimension magnified image. So these two are fixed, this one's not. And that's what happens when we're outside the focal length. Inside the focal length, we'll draw the picture. You're going to see, you're going to get a virtual image. And that's in a moment. All right, superstars. And here we have a convex lens. But this time we're going to put the object, or DO, inside the focal length. This is still a converging lens, so F is positive. Big note. Convex lens, concave mirrors, both have positive Fs. They're opposite. So I'm going to draw my focal points to be relatively around the same. And here's my object. Doesn't matter how big or how small it is. Just like with the mirror, if it's inside the focal length, it's going to make it a virtual image because light can't form unless it's beyond the focal point. With a virtual image for lenses, lenses have light going through. So a virtual image should be on this side. And if it's virtual, should it be upright or inverted? You got it, upright. So I'm going to expect something over here. 2 rays to draw. Ray number 1, through the middle, focal point down. Next one, just like with the mirror, we're going to line up the focal point and the tip. So it hits the lens and then it's going to go straight. Your eyes again over here for a mirror. You look through a lens. For a mirror, your eyes on this side. You see these two beams as coming from somewhere over here. I'm taking these two light beams and I'm making them extend back. I'm using dotted lines to show that. And here is that point. It is virtual for 3 reasons. It is upright. It is behind the lens where light shouldn't be. And finally, this is the point where light is scattering from, not combining from. As a reminder, negative DI. So for a lens, this over here is a negative image distance because it's not where it should be for a lens. HI is positive. This is going to be upright. HI again is positive. And finally, this thing is definitely magnified. Which means, well, M in this case is positive because it's upright. And the absolute value of M is going to be greater than 1. It is larger than 1 numerically. If I were to move this object and place it right here, this image would suddenly appear flipped down on this side. So already we know a couple things. Virtual images for lenses are in the top left area. Real images, because they're always down below and through, are down here. For a mirror, real images are down here and virtual are up here. So all 4 quadrants are taken with the principal axis and the lens and mirror. Cool. We're now going to show the last lens situation, kind of summarize it on a little table, and be done. I look forward to seeing you. All right, and here we have a concave lens. Just like a convex mirror, this is a scattering, so F is negative. You may have to add that in mathematically if you're asked to do a problem with a concave lens. And just like a convex mirror, this will always end up virtual, upright, and reduced because of the fact it's scattered. Two focal points, but these are virtual focal points with negative focal lengths. So light's not going to combine here, light's going to scatter from there. And now I'm going to draw my object. Doesn't matter if it's left or right of the focal point, this is always true. First beam. Straight to the middle, and now it's going to scatter. It can't go down to the focal point, it's going to go away from this focal point. I'm drawing dotted lines and straight lines to kind of show that. Straight, then away from the focal point. The second one we're going to draw is a little bit different. This is the unique one. We're going to draw the second line going from the tip, then going through the middle of the lens, and because of its curvature, it's not going to bend at all. These two light rays are what your eye sees. You see them as coming from right here. This is virtual because it's upright. It's virtual because of the fact it's behind the lens where it shouldn't be, and the light isn't actually combining here. This light is scattering from that point. It's reduced, upright. So with this kind of lens, you'll always get images right here. With that being stated, I now would like to kind of make a little overall table of all the different relationships here and have it as a reference point for you. Let's go. And welcome back. Here's a good little summary of what we've done so far. On the top, I've combined the real and inverted, the virtual and upright terms kind of together because they're linked. And you can see for real inverted, it's left of a mirror, that area, right at the lens, which means it's inverted. For virtual and upright, virtual is left of lens, right of mirror, and also upright. Magnified and reduced are their kind of own separate categories, so leave them separate. And these are the situations you can see for lenses and mirrors. So for a convex mirror, you will always get virtual, reduced, and upright. For a concave mirror, if it's inside the focal point, you get virtual, upright, and magnified. Outside of a focal length, you get real, inverted, and then it depends on what everything else is. You can see with this arrow that a concave mirror has the same situations as a convex lens, and a concave lens has the same situations as a convex mirror. By knowing the pictures, by being able to do the math with me in class, and by knowing this, you will be prepared for your quizzes, your partner problems, and eventually your final exam. Take a look, pause, write if you need something. I look forward to seeing you later on in physics. Have yourself a good time.